Well, good afternoon. It is Chemistry B, Unit 8. We're continuing about redox and equilibrium reactions. Today is day 2, reversible reactions, equilibrium, and Le Chatelier's principle. Let's get started. Ignore those arrows till we get there. First of all, what is a reversible reaction? Well, we'll get to that in just a second. But contrary to what we have seen, reactions usually do not just go completely from the reactants to the products. Most of the time we've talked about so far to this point reactions where A plus BC produces AB plus C. Well, that's not entirely the case. Some reactions are reversible, and what that means is that as reactants are being made into products are also then decomposing again back into reactants. So it's a conversion of reactants to products and the conversion of products to reactants, and that is taking place simultaneously. Now we show this using a double arrow. All right, so let's take a look. Here's a forward reaction of sulfur and oxygen. So we have 2SO2 plus O2 produces 2SO3. Now as a reversible reaction, that's the forward reaction. But we also have the reverse reaction, which is the decomposing of 2SO3 back into 2SO2 and O2. All right, so in the first reaction, read left to right, sulfur dioxide and oxygen produce sulfur trioxide. That's called the forward reaction. In the second reaction, read right to left, sulfur trioxide decomposes into oxygen and sulfur dioxide, called the reverse reaction. If we were to draw this reaction, we would draw two arrows in between the forward or the reverse reaction. We wouldn't have to write it twice. We would just superimpose a double arrow system like you see in bullet number 2. All right, and here is a pictorial of that reaction. SO2 plus O2, they are not at equilibrium. Now, what is equilibrium? Well, see if you can figure out what equilibrium is here. All right. 2SO2 plus O2 producing 2SO3 plus we have that reversible reaction there shown by the double arrow. It's at equilibrium. And then over here at the right we have SO3 not at equilibrium. So what is equilibrium? Well, equilibrium is when all three molecule types are present. Picture on the left, the first square. We have no SO3. Picture on the right. We have no SO2 and we have no O2. Picture in the middle, we've got all three. We've got molecules of SO2, we have molecules of SO3, and we have O2. All right? I forgot to go through and lowercase or superscript or subscript, the 2 and the 2 and the 3. So just understand that's SO2 and O2 and SO3. All right. So when the rates of the forward and reverse reaction are equal, a state of balance has been achieved, and we call that chemical equilibrium. Now, no net change occurs in the actual amounts of the components of the system. Take a look. If you can count up there, you will see oxygen is the red balls, all right? And if you count all of those up, we'll take a look at the left-hand picture. You count those up and we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 oxygens on the left. And in sulfurs, we have 1, 2, 3, 4, 5, 6 sulfurs. Take a look at the middle. 1, 2, 3, 4, 5, 6 sulfurs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 oxygens, and the one on the right you would count the same. So no net change occurs in the actual amounts, and you should realize that because all chemical reactions are just a changing of reactants to products, and the amount of the components or molecules are not lost. All right. What factors will affect equilibrium? Well, this is Le Chatelier's principle, and I'm going to really need you to concentrate on this. All right, because it's not very difficult if you're really paying close attention. All right, there's a delicate balance which will exist in a system at equilibrium. Almost any change will upset the balance, but the system does try and restore balance. But that generally increases or decreases the amount of products and reactants. Le Chatelier, in his principle, proposed that stresses that upset the equilibrium of a chemical system include changes in concentration. The amount of any reactant or product change causes the system to adjust to minimize the effects. So, adding or subtracting of a reactant or a product to the system will upset the system. It will cause the system to adjust to minimize the effects. How does this take place? Well, let's take a look. When more reactants are added, so let's say letter A and or B is added, the equilibrium shifts to reduce A and B by producing more C and D. So when you manipulate the reactants, more product is produced. Let's say I added more products to the system. When more products, C and or D, is added, the equilibrium shifts to reduce C and D by producing more A and B. So when you're adding or subtracting on either side of the equation, whether it's on the reactant side or the product side, Le Chatelier principle says the system wants to get back to stability. It wants to get back to equilibrium. So it will do what it can to do that, to try to restore balance. And to do that, they add or subtract the if you add more reactants, it's going to make more products. If you add more products, it's going to make more reactants. So it's kind of like a teeter-totter effect. If you add more reactants, the teeter-totter goes up. So the P would go up because it would be making more. If you add more product, it goes down. So as you can see right here in the teeter-totter diagram that we've got, okay, we have more reactants than product. When I add more reactants to offset it, more products would be made. So it would go up. If I add more products, like it is already now, I've done that, more reactants have been made. Okay? The second factor that upsets the balance will be temperature. An increase of temperature causes the equilibrium position of the reaction to shift in the direction that absorbs the heat. So let's take a look. If I increase the temperature in the reactant, in the system, all right, the position of equilibrium moves to the left. All right, so that means more A and B is going to be made. If you take a look at this, if the position of the equilibrium moves to the right, if you decrease the temperature, okay, so if I decrease the temperature, the position of equilibrium moves to the right. All right. The third factor is pressure. Concentration is number one. Number two is temperature. Number three is pressure. Changing the pressure on a system only affects gaseous equilibria that have an unequal number of moles or reactants and products. That's a pretty important concept. Only affects gases, and they better have an unequal number of moles of reactants and products. If they're equal or if they're not a gas, you're not getting a change. You're not getting a effect. Okay? So if you increase in pressure, it shifts the equilibrium toward decreasing the volume because you have lesser number of gaseous molecules. The position of equilibrium moves to the left, which is toward the reactant side, if you decrease the pressure on the reaction. So, increase the pressure in a reaction, the equilibrium position shifts toward the product, so more products will be made to offset that. Vice versa, if you decrease the pressure on the reaction, then more products or reactants will be made. All right, and that is the end of our day 2 topic.